For this lab, I threw a tennis ball against a wall. In this lab, I used the energy principle, Newton's second law, and the conservation of momentum to model the motion of a tennis ball undergoing a collision with a wall. I determined that the collision was inelastic. I also used the model to predict when the tennis ball will land, and compared it to when it actually landed. Here's the video of me throwing the ball against the wall. We see that the tennis ball hits the wall and bounces straight back and lands a little behind my feet. Here's the tracker video. I plotted the center of the ball in each frame for 24 frames. We see that around frame 7, the ball undergoes a collision with the wall. I found that the mass of the tennis ball was about 0.058 kilograms. The starting velocity was negative 17.445 meters per second in the x direction and 1.217 meters per second in the y direction. The starting position was the origin. I also used the gravitational constant negative 9.8 meters per second squared. Using the equations F net equals ma, final velocity of the ball equals initial velocity of the ball plus F net divided by the mass of the ball times the change in time, final position of the ball equals initial position of the ball plus velocity of the ball times delta t, F net equals the change in momentum over the change in time. The change in kinetic energy equals 1/2 mass of the ball times final velocity squared minus 1/2 mass of the ball times the initial velocity of the ball squared, and change in momentum equals 0, we can create a computational model of the data. First, though, we must calculate the force that the wall exerted against the ball. I used the equation F net equals dp dt. I estimated that the collision occurred over the time of about 0.03 of a second. I set the final velocity to be 9.196 meters per second and the initial velocity to be negative 17.174 meters per second. With that, I calculated that the wall exerted a force about 51.95 newtons against the wall. Also, I can calculate whether the collision was elastic or inelastic. Using the change in kinetic energy equation and the same final and initial velocities as before, I calculated that the ball lost about 6.154 joules of kinetic energy. Since the change in kinetic energy is not 0, the collision is inelastic. If the change in kinetic energy was 0, then the collision would be elastic. In real life, almost no collisions are ever elastic. Most of the time, some type of kinetic energy is transformed into something else. In this case, some of the ball's energy is transferred to the wall as vibrational energy that is then transferred to the earth. Next, I plugged the information and equations into VPython. I used the equation ball.velocity equals ball.velocity plus F net divided by ball.mass times delta t, and ball.position equals ball.position plus ball.velocity times delta t to calculate the position and velocity of the ball. I used 3 while loops, the first for the period of time before the ball hit the wall, the second for when the ball was undergoing the collision with the wall, and the third for when the ball was traveling away from the wall. Here we see the path that the ball travels, according to the computational model. Now we will compare the computational and actual models of the x and y positions of the ball, as well as the x velocity of the ball. In all of the graphs, the dashed line is the computational model and the dots are the tracker data. Here is the x position of the ball. We see that the computational model overestimates the position of the ball. This is because I did not account for drag in my computational model. Otherwise, it is a fairly good model. Here's the x velocity of the ball. Here we see why the x position graph was skewed. We see that the computational model assumes that, with the exception of the collision, the ball had a constant velocity, when in reality the magnitude of the velocity was decreasing. Here is the y position of the ball. We see that the computational model greatly overestimates the position of the ball. It expects the ball to hit the ground, which is located at negative 1.5 meters in the graph, almost a full second before it actually does. There are a variety of reasons for this. First, the camera angle was not directly straight on. Also, I did not throw the ball perfectly straight. I also assumed that the wall did not exert a force at all in the y direction. This would have been true if the ball had been at the top of its arc. However, it was not, and by this point the ball was already starting to come down. We can see in the graph of the tracker data that the ball appears to not move at all in the y direction at the time of the collision, while the computational model continues on like nothing happened. Also, just like for the x position, the ball experienced drag directed in the y direction. All these factors account for the computational model predicting the ball hitting the ground a second earlier than it actually did.